In this video, let us have a look at the addition reactions of alkenes, particularly the electrophilic addition reactions. Now, during the addition reactions of alkenes, the pi bond on the alkene is broken, the sigma bond on the reagent is broken, and then two new sigma bonds are formed. Okay, so a pi bond is broken, a sigma bond is broken, and two new sigma bonds are formed. Now, when the bond formation and bond breaking happens, heat is generated or heat is evolved. Now, the heat evolved during bond formation is greater than the heat evolved during bond breaking. And hence, the addition reactions are usually exothermic reactions. Alright, because the heat evolved during bond breaking is less than the heat evolved during bond formation. So, since during bond formation a lot of heat is evolved, the reaction will be exothermic. Now, there are three main types of addition reactions, or basically there are three types of addition reactions depending upon what is being added to the double bond. Now you have electrophilic addition reaction, nucleophilic addition reaction, and free radical addition reaction. Now we shall specifically take up electrophilic addition reaction here. So it will be an electrophile which will be getting added onto the double bond first. Alright, now the alkenes have a pi bond, and the electrons on the pi bond are diffuse in shape and are less firmly held onto the carbon nuclei. And therefore, this pi bond is susceptible to electrophilic attack. And that's why most of the alkenes undergo electrophilic addition reaction. Now, another way of explaining this is, you have an electron cloud around the pi bond, and an electron deficient electrophile can easily come and attack, or the electron cloud can easily attract the electrophile towards itself. So, alkenes are susceptible to electrophilic attack because of the pi electron cloud around the pi bond. You can add hydrogen, you can add halogen, you can add HX, hydrohalogen, you can add H2SO4, you can add water. All these addition reactions or addition of all these reagents to the double bond or to the alkene usually goes via the electrophilic addition method or electrophilic addition mechanism. Now let us take up the first one, hydrogenation, adding hydrogen onto the double bond or onto the alkene. So this you can depict the reaction this way. Now you can see here there is the presence of catalyst. Okay, so a catalyst is necessary to add hydrogen onto the double bond or onto the alkene. Usually we call this reaction as the reduction of alkenes. Alright, so usually the catalysts used are palladium or platinum. Even nickel is also used. We say palladium, hydrogen over palladium, hydrogen over platinum, etc. Okay, now the addition of hydrogen onto the double bond is syn addition. That is, both the hydrogen atoms are added up from the same side of the double bond. Now we shall see the mechanism and understand why it is a syn addition. Now look at the mechanism. You have the metal surface, the catalyst surface, onto which the hydrogen atoms are attached. Alright, the hydrogen molecule comes and the hydrogen atoms get attached to the metal surface. The alkene also gets attached to the metal surface. Now what happens? A hydrogen atom from the metal surface is transferred to the alkene. Alright, now a second hydrogen is also transferred to the alkene from the same side. Okay, that's why it is a syn addition. Alright, so the two hydrogen atoms are added from the same side of the alkene. Thus, you get a saturated alkene via syn addition. So this picture I've got from Lumen Learning. You can view this picture in that website also. All right. So because hydrogenation is catalytic hydrogenation, or you can say we use catalyst. In fact, it's a heterogeneous catalysis which is happening. So the metal catalyst, onto the metal catalyst, the hydrogen and the alkene gets adsorbed, and it is from the surface of the catalyst that the hydrogen is getting added up onto the alkene, and that is a syn addition. Alright, now coming to halogenation. Now in halogenation you have a different story. Now in halogenation you don't need a catalyst. Catalyst is not required. Okay, and you get vicinal dihalides. Okay, if you're using chlorine, you get vicinal dichloride here. Now the halogens which can be used are usually bromine or chlorine. They are the best halogens used for halogenating alkenes. Fluorine does not undergo halogenation, or is not a good candidate for halogenation, because fluorine reacts vigorously and several other oxidation products are formed. Sometimes it may even be, the reaction may be even explosive. Addition of iodine also to alkene also in this way is thermodynamically very slow because of the large size of iodine atoms when compared to bromine and chlorine. Alright, so usually halogenation of alkenes are easily done with bromine and chlorine. And you get 1,2 dihalides, dibromides, 1,2 dibromides or 1,2 dichlorides. Their vicinal dihalides are obtained. Now, halogenation, if you need to add up both the halogens onto the double bond, you will have to use non-nucleophilic solvents like chloroform. What will happen if you use non-nucleophilic or aqueous solvents, we shall see later on. Addition of halogens onto the alkene is stereospecific, and the addition is anti-addition. We have seen that hydrogenation, or hydrogen gets added up onto the alkene by syn addition, but here it is anti-addition. And cis-alkene will give us a mixture of enantiomers, and trans-alkene will give us a meso compound. So as an example, you have here malic acid, which is a cis compound. You get racemic mixture or mixture of enantiomers. You get SS and RR as the product. While if you use the fumaric acid, the trans compound, you get a meso compound as the product. Alright, so here the cis compound is giving us a mixture of enantiomers, and trans compound is giving us a meso compound as product. So the reaction of addition of alkene or halogen onto alkene is stereospecific and anti-addition. We shall see the mechanism of this addition reaction. And when we look at the mechanism, see the bromine is getting added on to the alkene. See, a bromonium ion is formed here. Or if you're using chlorine, you get chloronium ion. You can say halonium ion. For addition of halogens. All right. So first, the in the case of bromine, the bromine compound, the bromine molecule is polarized, and one bromine atom gets partial negative charge, and the other bromine atom gets partial positive charge, and the positively charged bromine gets added on to the double bond, and a bromonium ion is formed. Once a bromonium ion is formed, the negatively charged bromine attacks any one of these carbon atoms. Okay, and then you get the dibromide, vicinal dibromide. Now this bromonium ion is, or halonium ions are planar cyclic intermediates, bridging the original pi bond of the alkene. And this, since the bromonium ion or halonium ions are formed, that is responsible for the anti-addition of the alkene onto the, halogen onto the alkene. So the formation of halonium ion is the reason for stereospecificity and the anti-addition of halogen onto the alkene. Because the top part is blocked, the bromide ion or the nucleophilic bromine can attack only from the opposite side of the attack of electrophilic bromine. Now, if halogenation is carried out in aqueous solvents, or in the presence of water, or in the presence of nucleophilic solvent like water or alcohol, what happens? Now here you can see first the bromonium ion is formed, then instead of the bromide ion, the negatively charged bromine ion, the water molecule or the alcohol will be attacking, the nucleophile will be attacking, because this will be a stronger nucleophile than our bromide, and you get halohydrins. Okay, here you get bromohydrins since you are using bromine. If you are using chlorine, you get chlorohydrins. And they again will be enantiomers, as we said earlier. Any of these, the attack will be anti. Now, here you have the formation of tertiary carbon atom and secondary carbon atom. Since you are using asymmetric alkene over here, so when after the formation of bromonium ion, if the nucleophile attacks onto this carbon, then it will be a tertiary carbocation which will be formed. And if the nucleophile attacks onto this carbon, a secondary carbocation will be formed. So the water molecule will attack the more substituted carbon atom. So you can say that it is regiospecific, or the nucleophilic attack the more substituted carbon atom. So when you're using an unsymmetrical alkene, and if you have another nucleophile other than halogen is present, then you will find that the nucleophilic attack will be happening on the more substituted carbon atom. Alright, so in the formation of halohydrins, instead of water and halogen, you can even use HOCl or HOBr, which are generated in situ by the reaction of water with chlorine or bromine. And sometimes HOI also attacks gets added up onto the double bond. So if you want halohydrins, you add first the halogen, and then you add the halogen in presence of water, you get halohydrin. If you want only dihalides to be formed from the alkene, then use non-aqueous solvents while adding the halogen. Alright, now these are a few examples of addition of bromine onto the double bonds. You can see here you get enantiomers mixture over here as the products. Looking at the next reaction, hydrohalogenation, that is addition of HX. X can be iodide, chloride or bromine, and when you add a hydrogen halide onto alkene, the hydrogen and the halogen gets added up across the double bond. And the HX will be HX bond will be polarized. H will be having partial positive charge. X will be having, or the halogen will be having partial negative charge. And it will be the hydrogen which will be getting added up onto the double bond first. Now, this is the case with the symmetrical alkene. Now I'll show two more examples. Here you have unsymmetrical alkene. Alright, these two alkenes are unsymmetrical and you're getting alkyl halides in this manner. That is, you're getting Markovnikov's product, or the products which are obtained are Markovnikov's product. The hydrogen halide gets added up onto the double bond based on Markovnikov's rule. That is, the hydrogen of the hydrogen halide or HX gets added up onto the carbon with more number of hydrogen atoms. And the negative part, or the halide ion, gets added up onto the more substituted carbon atom in the alkene. Now, when we look at the mechanism, it will be clear why this alkene or such unsymmetrical alkene gives only Markovnikov's product. Now, when we look at the mechanism, what we find is the hydrogen gets added up across the double bond onto the carbon and a carbocation is formed. Once the carbocation is formed, then the bromide ion or the halide ion gets attached onto the cationic carbon. And you get the halide or alkyl halide. Now, the hydrogen is getting added up onto the carbon, which is less substituted. Now, why is that so? When the hydrogen gets added up onto the carbon, which is less substituted, we get more stable carbocation. So you can see here, because of this, we can say that addition of HX onto the alkene is regioselective, because the electrophilic part and the nucleophilic part selects the region of its attachment. Hydrogen selects the region, that is the carbon having more number of hydrogen atoms, and the halide ion selects the carbon which is more substituted. So this reaction is regioselective. Unlike the addition of halogen or hydrogen, we have a regioselectivity in this case. Now let us see why is that so. Now, if the hydrogen is getting added up onto the alkene or onto the carbon which is more substituted or with less number of hydrogen atoms, then you get this carbocation. And if the hydrogen is getting added on to the carbon which is less substituted, you get this carbocation. And you find that the second carbocation is more stable. So when the hydrogen gets added up onto the carbon which is less substituted, you get a stabler carbocation. And formation of the stable carbocation is the rate determining step in this reaction. So in order to get a stable carbocation, the hydrogen gets added up onto the carbon which is having more number of hydrogen atoms, or in other words, which is less substituted. And easily the halide ion can attack this carbon. So there are two modes of attack here, the possibilities. One is syn addition and this anti-addition, because we are producing, or during the reaction, a free carbocation is produced. So the incoming nucleophile can attack from the side from which the hydrogen has attached, or from the side opposite to which the hydrogen has been attached. So you get syn addition product and anti-addition product, or rather you get a mixture of enantiomers. Okay, so the hydrogen and the halogen can get added either from the same side or from the opposite side. In case of hydrogenation, it was syn addition. In case of halogenation, it was anti-addition. In case of hydrohalogenation, you can have both syn addition and anti-addition. So you get a racemic mixture. So the reaction is regioselective and you get a racemic mixture. Now another example for regioselectivity, showing regioselectivity of hydrohalogenation, is here. The major product is this compound, the first compound, wherein the bromine, the halide ion, is getting attached onto the carbon which is more substituted. So you get two regioisomers, of which one is major product. So the reaction proceeds via the most stable carbocation. It follows Markovnikov's rule. Now, anti-Markovnikov product is also obtained provided you carry out the reaction in the presence of peroxides. When you carry out the reaction in the presence of peroxide, the halide ion gets added on to the carbon which is less substituted. You call it as anti-Markovnikov addition. That's because there is in the presence of peroxides, the reactions proceed via free radical mechanism. We'll be discussing this later on. Alright, and this is seen only in the case of HBr, not observed with HFHCl or HI. So usually with hydrogen halides you get Markovnikov product, but if you are carrying out addition of HBr in presence of peroxides, you get anti-Markovnikov product. Now, during this addition reaction, rearrangement of the carbocation is also possible, or you can get rearranged products. So if we said that we get a positive or a free carbocation is generated during this reaction. Now, this free carbocation, if it is possible to stabilize this free carbocation via hydride shift or methyl shift, then that will happen, and then only the halide ion will attack the carbocation. So here you have a secondary carbocation. This carbocation can undergo a hydride shift to produce a tertiary carbocation, and then the halide ion will attack. So you get a rearranged product. Even though the expected product is a different one, you get a rearranged product over here. Alright, that is, all these shows that the mechanism goes via formation of carbocation. So here you get 40% of the normal Markovnikov product and 60% of the rearranged product. Now here the carbocation formed is this one. This is a primary carbocation. This can rearrange to secondary carbocation, and if there is a chance, the secondary carbocation. Another example. The secondary carbocation here. This primary carbocation. If there are 3 methyl groups attached, there can be alkyl shift and formation of tertiary carbocation. So wherever the rearrangement is possible, the carbocation will undergo rearrangement, resulting in the formation of rearranged alkyl halides. So all these are possible in asymmetrical alkenes. So nature of the substrate also decides the product. Now let us see the reaction rates, how the different factors affects the reaction rate. The hydrogen halide affects in this way, that is HF reacts faster. With HF the addition will be faster and it goes down, will be slow, I'm very sorry. With HF the reaction is slow, but with HI it is very fast. Now the reason is because of the variation in the strength of HX bond. We know that HI bond is weak when compared to HF bond. So HI can be broken easily and the reaction can be carried out very easily with HI. That's why the reaction rate of hydrohalogenation with HI is maximum, because the hydrogen is loosely bound to iodide and hydrogen can easily attack the double bond. Now, in the case of substrate, the reactivity increases with substituted substrates. More the substitution across the double bond, particularly alkyl substitution across the double bond, more will be the reactivity, because the stability of the carbocation increases. It need not be alkyl group alone, it can be any electron donating group which is attached on the double bonded carbon atom. Then the reaction will be faster because the carbocation formed will be stabilized. And also the reaction product is decided by the nature of nature of the substrate, because if there is a possibility for rearrangement, that will also happen. Alright, so the nature of the reagent as well as the nature of the substrate decides the rate of the reaction, particularly hydrohalogenation. Now, next reaction is the addition of sulfuric acid to alkenes. when alkenes are reacted with concentrated sulfuric acid, you get alkyl hydrogen sulfates. Okay, this again is the same way. The addition is the same way as of addition of HX onto the alkene. Hydrogen gets added up first, and then SO4 minus gets added up next. Now, this hydrogen sulfate, when treated with water, will produce alcohols. So this is one way of production of alcohols. You treat the alkene with water in the presence of acid. Okay, it's the same thing. Addition of hydration of alkene also comes here. Now, but if we are using highly concentrated sulfuric acid, if the concentration of sulfuric acid is very high, maybe above 60% of sulfuric acid, then the alkene undergoes condensation and polymerization. Chances of polymerization is there. Now you see here, the proton gets added up onto the alkene and you get the carbocation. Then instead of the nucleophile, the alkene attacks the carbocation. And dimer is formed. To this again another alkene gets attached, and like this polymer will be formed. Now if you control the concentration of alkene, you can restrict the chain length of the polymer. Alright, so this is called self-condensation of alkene in the presence of sulfuric acid. Remember, the concentration of the sulfuric acid in this case must be very high. Coming to the next reaction, the last one under this discussion, that is hydration, addition of water onto the alkene. Now, in water you have the H and the OH. They will be added across the double bond. In H2O, H plus will be there and OH minus will be there. H plus gets added up first, followed by addition of OH minus. So here the reaction happens in the presence of acidic medium. When you use water alone, the reaction will be quite slow, but the reaction can be hastened or the rate can be increased by the addition of acid or Lewis acid. Now we have seen earlier the reaction of sulfuric acid. If you dilute sulfuric acid or sulfuric acid, first add sulfuric acid followed by addition of water, you get alcohol. It's almost the same thing what's happening here. When you add water onto the alkene, you get alcohol. Now, the reaction, as I said earlier, it can be catalyzed by Lewis or Bronsted acid. Now, when we look at the mechanism, it follows the same. The mechanism is the same as that in the case of addition of HX and H2SO4. The proton first gets added onto the across the double bond, and a more stable carbocation will be formed. So first it will be protonation, proton transfer, followed by addition of the nucleophile. The water molecule or the nucleophilic water molecule gets added onto the stable carbocation. Then again another proton transfer happens from the added water onto the water in the solvent. Okay, and a proton transfer happens from the oxone. You can say this is the oxonium ion which is being formed. And after the proton transfer from the oxonium ion, you get the alcohol. Now this reaction also is regioselective. It follows Markovnikov's rule, and it gives racemic mixture because a free carbocation is formed. So your nucleophile or the water molecule or OH minus can be added up from any side from the same side of the attack of hydrogen or from the opposite side of the attack of hydrogen. So you get the reaction is regioselective and you get a racemic mixture. So we have seen that when we look back, the addition of HX, H2SO4, H2O all follows the same mechanism. Formation of carbocation intermediate, and it's regioselective and we get racemic mixture. Addition of bromine is addition of hydrogen follows syn addition, while of halogen follows anti-addition. And when a halogen is added onto the double bond, you get enantiomers. Cis compound gives enantiomers, and trans compound will give you meso compound as a product. Addition of hydrogen halide is regioselective, and we get a racemic mixture because there is formation of carbocation, free carbocation. In the case of reaction with halogen, you get halonium ion as the intermediate, tricyclic intermediate is formed. Now when you add H2SO4 again, it is regioselective and you get racemic mixture. Same is the story with H2O, water, addition of water. Here the reaction is regioselective and racemic mixture. So this is in brief regarding the addition reactions of alkanes, addition of various compounds onto the double bond. Hope it's clear to you. Thank you.